So, hello ma'am, I'm Karthick Raghul and I'm here to present my digital assignment 3, and I have taken the topic from theory of computation, and my question is the variance of finite automata, and here we can see the sub questions as two-way finite automata, multi-head finite state automata, probabilistic finite automata, weight finite automata, and digital images. Okay. So first of all, what is a finite automata? So we can say that finite automata is a simple idealized machine which can be used to recognize the patterns within the given inputs taken from some character set or an alphabet. So the job of a finite automata is to accept or reject an input depending on whether the pattern defined by the finite automata occurs in the input or it is rejected. So it is actually used in text processing, compilers, and hardware design. So CFDs are used in programming languages and also used in artificial intelligence. So CFDs are originally first of all were used in the study of human languages. So we can see the application of finite automata. It is used in various fields, such as it is used in text editors, used for spelling checkers to recognize the pattern using the regular expressions, and it can also be used to design the lexical analysis of a compiler. So first, what is a two-way finite automata? So two-way finite automata, it was first introduced in the early 1960s. In 1959, it was introduced by Rabin and Scott, and they proved that the two DFAs have equivalent power that of a one DFA. So in two DFA, any formal language which can be recognized can also be recognized by a one DFA. So its definition is as follows. A 2DFA is an abstract machine which is a generalized version of the 1DFA which can revisit all the entire characters which are already processed by the machine. So as in 1DFA, there are a finite number of states only with transition between them based on the current character. But in that each transition is also labeled within a given value, indicating whether the machine will move its position to the left or right or stay the same. So the equivalent 1DFA for 2DFA may require many exponential states, and so it makes generally it makes 2DFAs more practical representation for algorithms for common problems. So it can be the two DFS can be used in many algorithms to solve common problems. So we see the abstract of the two DFAs. So here we study the relationship between size of two-way finite automata, accepting a language and its complement. And in the deterministic case, for a given 2DFA with n states, we'll build an automata accepting the complement with at most 4 n states, independent of its size of the input alphabet given to it. So, for a non-deterministic case, using a variant of inductive counting, we show that the complement of a unary language accepted by a n-state two-way 2NFA can also be accepted by a word-state NFA. Here we can also make the two NFAs as a halting state. So a two-way deterministic finite automata, it can also be described in the form, and here we can see Q is the finite non-empty set of states, epsilon is finite and it is also non-empty set of input alphabet, L is the left hand marker and R is the right hand marker, and S is the start state, T is the end state, and R is the reject state. And delta is, we can see that Q into left hand marker and right hand marker. It can also state that once the automata reaches the accept or reject state, it stays there forever, and the pointer goes to the rightmost symbol. So, and then it cycles. So this process happens repeatedly, infinitely. So two-way non-deterministic finite automata. Here, 2NFA is the multiple transitions defined in the same original configuration. So you can see the transition function here. So like the one NFA, two NFA is also accept a string if at least one possible computation combination is accepted by it. So two-way alternating finite automata. It is a two-way extension of a alternating one AFA. Two AFA is an extension of a one AFA, and its set state is defined as follows. And in this extensional state, a two NFA non-deterministically chooses the next state like an NFA, and it also accepts at least one of the resulting completion. So we can see that two AFA also accept if at least one resulting completion accept. So it is same that of the two NFA. So next topic is multi-head finite state automata. And multi-head, it was originally introduced. It was also introduced by Rabin and Scott 5 years after the two NFA introduced. It was introduced in 1964. So a vast knowledge on computational and descriptional complexity issues on the multi-head finite state automata or documenting its importance were developed since then. So although its concept is simple, the behavior of them in the computation it can be complex and may lead to many undecidable problems such as university equivalence, etc. So these many strong negative results trigger the alternative characterization of the multi-head finite state automata. So these alternative models can be used for the better understanding of the multi-head finite state automata. So multi-head finite state automata is defined as follows. And here is S is the finite set of internal states, A is the set of input, and K is the number of heads, and left and right hand markers. S naught is the starting state and initial state, and F is the set of accepting state. That is the final state. So delta is partial transition function. So here the power of the multi-head finite automata, it is well studied on one-head machines, and for the one-head machines, we can obtain a characterization of a family of regular languages. So here we can see the alternative models of multi-head finite state automata. Here I have mentioned only three models, which is most useful for the alternative of multi-head finite state automata. Here I have mentioned multi-head automata accepting the bounded languages, the data independent or oblivious multi-head finite automata, and parallel communicating finite automata. So next topic is data independent multi-head finite automata. It can generally be used in Turing machines, and it was originally introduced in 1974. So the oblivious of automata, it was investigated in relation with other. It was first investigated while comparing with the other computation models. So parallel communicating finite automata. It it is first introduced in early 2000s, in 2002, and let us say a parallel communicating finite automata of degree k is a device k finite automata working in parallel with each other in a common one-way read-only input tape, and it is also synchronized according to the universal clock. A K automata communicate on request by the states when some automata enters in a distinguished heuristic Qi. It is said to return to the current state of automata. Let us say the current state as AA. So since the next state of sender is AA, we distinguish the previous two modes. And in the non-retaining mode, the sender remains the current state, whereas in the retaining mode, the sender is set to return to its initial state. Now the next topic is probabilistic finite automata. This was actually introduced by Michael Rabin in 1963, and it is also known as the Rabin automata. After it is named after his name. So in recent years, a variant has been formulated in terms of quantum probabilities, and it is also known as quantum finite automata. So normally in mathematics and computer science, it is the probabilistic automata. It is used in a generalization of the NFAs. So than computer science, it can be very useful in mathematics. So because by taking in the translation function, it can give the equivalent translation matrix for it. So its definition is as follows. In the particular, the state of the probabilistic automaton is always a random vector. Since the product of any two random matrix is random only, so we take the probability, we take the product of any two random matrix, so it can be random, and the product of a random vector is again a random vector only. So these vectors can also be called as the distribution of states. So generalizations, the probabilistic automata has a geometric interpretation. That is, the state vector can be understood to be a point that lives on the face of a standard simplex. That is it. Resides in the edge. A transaction function from a monoid will be acting on a point, and this may be generalized by having that point be some general topological place, while the transaction matrix are chosen from collection of operators acting on the specific topological space. So quantum finite automaton example, we can say we can take that as a quantum finite automaton. So the application of the when we look at the application of probabilistic finite state automata, it is used in various research areas in pattern recognition and in the fields where pattern recognition is linked. So it is mainly used in pattern recognition. So it is also used in the fields of computational linguistics, machine learning, time series analysis, and circuit testing, computation biology, and so on. You can say. So it is generally used in various fields. Mhm. So we can say that. So the next topic is weight finite state automata. Finite state machines can be weighed where each transition is labeled with a weight in addition to its input and output labels. So a weight finite state automata over a set of k weights, we can say defined similarly to an unweighted one as a 9 tuple. So here a set of state T is defined as follows, and weight finite state automata. Here Q sigma T I F are all defined as follows. So what the generally what is a weight finite automata? It was first introduced by Schwarzenberger in 1994, and it was used for the domain of weights and their computation. So the algebraic structure of these theorems proved to be fruitful and very useful for all the scientists. This soon led to a rich mathematical theory, including application for a pure language of theoretic questions as well as practical application, and it is also used in the practical application of digital image compression and algorithm for natural language processing. So first, the starting point of weight finite automata is to determine the number of ways a word can be accepted. Thus, thus its behavior associates a quantity or a weight to every word. So it is specified as follows. We saw the set of states here, and here Q is a finite state of states. Epsilon is a set of alphabets. So it is used in representation of grayscale image using a weight finite state automata. It is um, very useful in the recognizing the digital images. So a grayscale image of a finite resolution. It is like it consists of 2 power m by 2 power m pixels, where the m is greater than 7 and less than 11 by a by a multi-resolution image, it means a collection of compatible 2 power n by 2 power n resolution image where n can be equal to 0, 1, 2 and so on. So then they assign the resolution to each pixel by a word of length n over alphabet epsilon 0, 1, 2, 3 and it can be so on. So then we can define that our final state image as a function f1. The function f1 of x gives the value of pixel at the address x. So a multi-resolution image is a function f1 where epsilon star defines the function r. Thank you.